We're now going to discuss derivatives in forces and moments in our pseudo-aerodynamic forces and moments with respect to translational acceleration. So these are the terms u dot, v dot, and w dot, okay? So what we're trying to capture here is the dependence of the aerodynamics on how rapidly we're changing our velocity along u, v, or w. And the aerodynamics of the aircraft depend on this because in a transient sense, it takes a finite time for the fluid flow or the effects of, for example, for the main wing to propagate downstream and affect the horizontal tail. So, for example, the horizontal tail is experiencing downwash from the main wing, and if we have a rapid change in W dot, which is associated with our angle of attack, then we can have a rapid change in the lift coefficient on the main wing, but it takes a minute for that effect to propagate downstream and for the downwash from that effect to propagate downstream. It takes some finite amount of time. And so the aerodynamics are not only a function of our actual velocities u, v, and w, but they're also a function of how rapidly those velocities are changing. So these are changes in u, v, and w with respect to time. Now, in a previous video, we actually already assumed that all of our dependencies on v dot, or changes with respect to v dot, are zero or negligible. Okay, so we're just going to drop those out for our analysis here and say that they're extremely small and negligible, or some of them are exactly zero. Changes in our forces with respect to v dot are zero. We're also actually going to neglect any changes in u dot. These are usually small, so those are also negligible as a first cut here, as a first approximation. And this isn't this really isn't too bad of an approximation. This is kind of a common thing to neglect these for the first cut. Now, to actually get real values for any of these, we would need very complicated CFD, so unsteady CFD simulations that can capture these transient effects, or to put this in a wind tunnel where we are, rapidly changing something about this aircraft in order to modify, or in order to estimate these types of effects on the vehicle. So anyway, measuring these or getting good estimates from these from CFD is actually not trivial. So that's why, as a first approximation, and it's really not too bad of one, we're going to drop out the u dot and v dot terms and assume that those are zero, okay? However, for w dot, those can be more pronounced. And so we're going to walk through, actually, I'm not going to go through in detail the development. I'm following Phillips's book, his Mechanics of Flight book again, on this particular development. And he walks through in detail how he comes up with these approximations, but I'm just going to give you his solution for the approximation that he comes up for changes with respect to w dot. Now, these changes are very commonly referred to in the aerodynamics community as alpha dot terms. And that's because we don't usually think of things in terms of w dot. Just like instead of u, v, and w, we usually talk about things in alpha and beta and total velocity. Well, that's the same with the w dot here. We usually don't think of w dot, and instead we put this in terms of an alpha dot. So for example, we're going to have a change in, for example, the force in the z direction, the body force, with respect to w dot. And you can walk through a similar analysis to what we've done before to show that that is equal to 1 over v naught times the change in that force with respect to alpha dot. So here, what we've done is just swapped out, instead of derivatives with respect to w dot, we can use derivatives with respect to alpha dot, because we know how alpha dot and w dot are related, and that's through this 1 over v naught ratio here. Okay, so Philip says that can be approximated for a conventional aircraft. Now, for this conventional aircraft, let me just draw a little sketch over here. So here's our airframe, and we've got some main wing here, and then some horizontal back here. Okay, and so for this conventional aircraft, he says you can estimate that this change in the z-force, or basically change in lift with respect to alpha dot, and it depends on the lift slope of the main wing and the horizontal, as well as their distance between the two. So the distance, if we go from the wing tip here, we're looking at the distance from that wing tip back to the aerodynamic center of the horizontal, and that's what he calls LWT. Okay, that's that distance. It's positive if the main wing is in front of the horizontal, and so actually, if we're using our coordinate system here, where we're running from the CG, we have X body pointed out the nose here. The LWT is equal to X body of the wing tip, WT, minus the X location in the body coordinates of the horizontal. Okay. Okay, so with that definition, he says that this can be approximated as minus 1.1 or 10% higher than this ratio, rho times the area of the main wing times the area of the horizontal times LWT divided by pi b squared of the main wing, and then times by eta sub h. Again, that's the tail efficiency, or the ratio of the dynamic pressures between the main wing and the horizontal tail, and then multiplied by CL wing alpha times CL horizontal comma alpha. Okay, so that's the lift slope of the main wing multiplied by the lift slope of the tail. Okay, and likewise, the change in pitching moment, so that's my body with respect to W dot, is equal to, we can say that's equivalent to a change in that pitching moment with respect to alpha dot multiplied by 1 over V naught. And it's a very similar equation. It's equal to 1.1 times rho SW SH LWT times XBH. So here we're multiplying it. This is really the only difference between these two equations, and that's that we're multiplying it by this moment arm, XBH. That's the location of the horizontal tail. And then we're going to divide that by pi BW squared, and then that's times by eta sub h, and the lift slope of the wing times the lift slope of the horizontal. Okay, so these are just two approximations for the change in lift, or the change in the force in the z direction with respect to alpha dot, and the change in pitching moment with respect to alpha dot. And then the remainder, the other derivatives with respect to W dot or alpha dot here, we assume are 0 or negligible. Now, this is an approximation for a conventional aircraft. Okay, so let me just write that down. This is the approximation for conventional aircraft. And he says that if you have a canard design, so your horizontal is horizontal is actually in front of the main wing, then we just neglect this altogether and say that both of these terms are 0. Also, if you have a flying wing design, you would assume that these two are 0. And this is, again, just kind of a first approximation for these, because it's really challenging to get these numbers out of CFD or experimental data. So anyway, again, this is a first approximation. We've dropped out a bunch of terms here. All the U dot and V dot terms we've assumed are 0, or derivatives with respect to U dot and V dot. The W dot, we assume that all of those are 0 except for these two terms For conventional aircraft, we have a way to estimate these simply because it's rather difficult to get those out of other numerical methods. It can be done, and people are really good at CFD or experimentation can estimate these derivatives. But as a first cut, and certainly for this class, this is going to be sufficient for our needs.